So we sometimes have data sets where lines won't work, like this one. So what do we do? Well, we promise deep neural networks, and so far we just have linear regression and linear classification. So let's go deeper. So like we had in our cartoon earlier, we're going to take our inputs. We're going to compute some weighted sums, get what used to be called y. But then we're going to do it again. We're going to take those new values, and we're going to take more weights and compute new values, and so on. So one additional, really just one more thing to give us more or less everything about deep neural networks, to make sure that the whole thing doesn't just collapse to a single linear function. At every level, we're going to take our weighted sum, right, the sum of the y, w times x's, and we're going to add it all up, and then we're going to use what's called an activation function. Typically, what people use these days is that function up on the top right. It's really just max of your number with 0, right? So if it's positive, we keep it. If it's negative, we get rid of it and just replace it with 0. And so the mental model for this is that you can think of this at a very, 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 very high level as an analogy to a neuron, where if all your inputs, when you add them up with these weighted sums, give you a positive number, then this neuron unit thing, circle, activates. That's why it's called an activation function, and has a positive output. And if your input all adds up to a negative value, then it doesn't activate, and you just get a 0. And so that's how we're going to get this idea that some of the neurons, units, cells in your network are going to activate when certain features of your input are present, and others will activate when other features are present, and somehow, hopefully, you learn weights that make this do something useful. And that's basically it. That gives us deep learning, right? We have all these different layers. We have weights at each layer. We have activation functions at each layer. And then the idea is that you will actually be able to, like it says there, right, match the structure of the problem with the structure of your network. And so if you're doing vision, it's the easiest place to sort of think about it. Your initial layers will have units that detect lines and feature and textures and things like that. And your 10th layer in your network might actually be learning things that are much higher, more complicated visual features that you can actually use to combine to do recognition or classification or whatever you're doing. So coming back to this picture, right, that's what's going on at a high level, where you just have a bunch of weights, you have activations at each layer, and yeah, you have this hierarchy of features. So, well, yeah, let's quickly do this, right? So let's go back to our playground and actually use more hidden layers. So I guess I need to stop this. Where's my stop button? What's beeping? Right, so let's go back to this data set. It's not linearly separable, but if I add hidden layer, let's say with 3 neurons, I'm going to be able to compute 3 different lines.
Can I interrupt? The video link on your channel, is there a way to publish it, or does it automatically?
I think it should just get updated, and I can, if you have the link, just put it in Slack again. But
I mean, like I put the second session, but a couple of people are asking whether the channel gets updated. The channel they don't get updated.
Let's play with that at the next break, maybe. My understanding is it should get updated, but I don't know. Maybe there's a lag. Okay. Sorry, coming back to this. Right, so now we have 3 neurons that each can learn a different linear function. And then we can have more weights for each of these outputs and get a final output. One thing that maybe I should have just set, so don't worry about the details too much. For activation function, I'm going to use ReLU. That's a fancy name. Well, it's called rectified linear unit, which is a fancy name for max of 0 and x, right? It's that sort of linear, if the input's positive, 0 if the input's negative. Just so we keep things consistent to what I was talking about, right? And so here you can see, okay, this one, currently with the initial random weights, where it's blue, it means the output's positive, and where it's white, the output's 0. And so sort of each of these is cutting off a different part of the plane. And if I hit the play button to run gradient descent, it's going to learn something hopefully vaguely plausible to actually classify this. Can anyone predict before I hit the play button what it's going to learn? Maybe you're already playing with it. Well, what does it learn? And why? With 3 neurons? Huh, that's interesting. Mine also learned a hexagon. Right, so how do they get a hexagon? It has this line. So where's this line? It has negative weights in all of them. Right, because you want positive values near the origin, and negative values far away. And so there's linear combinations of these things. And you get these lines because you only have three neurons, and each of them has a linear feature. But it's managed to put together something that kind of does a good job on this data set. It's kind of fun to try the same network on this data set. Right? It's 2 spirals next to each other, and so you have to figure out. The true model is pretty clear, right? Like you need to actually follow these spirals out to infinity. But if I train it like this, it's going to say, it's kind of hard for me to find good separation with just three lines that I'm then combining. So it's getting 55% of my data points correct in my training data. I guess we haven't gotten to test data yet, but if you're familiar with test data, you can see that it's not doing very well on a test set. It's still exactly 50%. So this is not enough capacity for that. All right, so we'll play with this more later when we have a little bit more tools to work with. But for now, let's come back to this. So one thing that I sort of skimmed over earlier was this notion of derivatives, right? We're doing gradient descent. So we have this, what is the gradient, right? It's a derivative of my error with respect to each of my weights. And now if I have a network with many layers, you want to ask the question, okay, how do I know what's going to happen to the error all the way at my output where the labels are if I change some random weight between the first and second layer of my network? And again, luckily, well, there's 2 things, right? There's this notion of backpropagation or algorithm that people came up with back in the 70s? Can't remember. Maybe it was the 80s actually, where if your nonlinearities, your activation functions, are continuous and actually more or less differentiable, the ReLU function is not differentiable exactly at 0, but it turns out that doesn't matter. As long as it's differentiable everywhere else, you can actually just use the chain rule from calculus and figure out, okay, here's what needs to happen at the last layer weights to reduce the error and sort of propagate that all the way back to some approximation. All the toolkits like TensorFlow, et cetera, will do this for you. So you don't have to actually worry about implementing the derivatives yourself. It is still important to keep this in mind because numerically it matters. In particular, if your derivatives are really small, as you if your network is really deep, then the effects of a weight change somewhere early in the network is going to be very diluted by the time it gets to the end. And so your network may train very, very slowly. So we'll see this again in practice as we play with the playground and as we look at some real examples. So it is still important in your head to know, okay, what's happening is backpropagation. I'm taking the errors at the end of my network and sort of wiggling the weights in the last layers and then pushing that further and further back. And the signal kind of attenuates as you go through. So summarizing, right? How does this work? We go back to our network. We take our inputs. We do what's called a forward pass. So we take our input, we multiply it by the weights. For the first layer, we apply the activation function. We get activations at the first layer. We multiply them by the next weights, et cetera, until we get probabilities. We compare them to the label for this thing. And we say, OK, that wasn't quite right. We want the probability of A to be higher. We want the other probabilities to be lower. And then we do a backward pass, where we say, OK, how do I change all the weights going all the way back so that the error goes down? And then we wiggle the weights a little bit, and then we repeat. So one thing that, again, I haven't talked about very carefully yet is, theoretically, if you just do sort of the correct gradient descent, what you should actually do is you should take all of your inputs, right? So if I have a training set of 100,000 letters, you want to compute the labels, the predictions for each of them, compute the overall error for your whole data set, right? So sort of how wrong am I on average? And then figure out how do I change the weights to reduce that overall error for my whole data set. Now, the problem is that means that every time I go through 100,000 examples, I only make one update to my weights at the end of the whole pass. And so that's incredibly slow at training. So what people do in practice is called stochastic gradient descent, where basically you take some small number of samples. Could be just one, typically more like, well, roughly speaking, as many as you fit in your GPU, like 128, 56, something like that. And you say, let me just compute the error on this small batch of samples, figure out how I can wiggle the weights to reduce the error on this batch, and just take those weight updates right now, and then keep going. So essentially, the way to think about this is you're getting noisy samples of the true sort of gradient on your whole data set, but they're close enough, and you can make so many more steps. If you think back to that walking around in the fields analogy, or in the hills, you can take lots and lots and lots of steps, even if they're not all quite downhill. They're sort of vaguely downhillish. That's better than figuring out exactly which direction to go before you can take a step. And again, as we see the code, we'll see this as a parameter, like how big is my batch size, right? How many things do I look at a time before I move on? And so you can actually play with the batch size in the simulator as well. So we'll do that later. Great, so we're pretty much done, right? We now have all the pieces. We can make a deep network. We can train it using this batch stochastic gradient descent to get low error in training data. Are we happy? I guess not. We still have to what? We still have 2 days, right? So what are we going to talk about if we're done? Yeah, so we talked about this a little bit during the break. Right, here's a learning model. I'm going to take my x-y pairs that you gave me. I'm going to memorize what y I should give for each of those x's. And if you give me some other point that I haven't seen before, I'll just give you a random answer. This learner, actually, it's kind of like a lot of kids in schools these days, right, can regurgitate what they've been told. 100% accuracy, right? Like, if you look at my training data and my training accuracy, it's perfect. However, it's useless, right? I already know what the labels are. I just told you them. What I want to know is if you give me a new x that I haven't seen before, right? A new image, a new audio file, a new point somewhere, what's the right answer for that point? And here is completely random. So we don't like that, right? If you come back to our cartoon, I don't want the correct kitten and puppy labels on the images I gave you. I want the correct label on new images. So how do we do that? standard machine learning thing of having a holdout sets that you use, so validation and test sets. What we're going to do is we're going to take our data that we have that's labeled, and we're going to split it. So we have some data that we call the training set, and we're going to have some other data that we call the validation set. And what we're going to do is we're going to train on the training data, right? So we're going to use gradient descent. We're going to compute errors, do forward, backward passes, et cetera. But we're going to see how well it's doing on the validation set. And if we at some point start to see that, the training error is going to keep going down, like gradient descent is going to sort of guarantee that. But if at some point we see that the validation error is no longer going down, or accuracy isn't going up, then basically, we need to stop because it's not generalizing anymore. And so we'll see this picture again tomorrow, I think. But you get curves that look like this. You have an accuracy curve in blue here, validation accuracy in green. And for a while, when you start training, they're both going up and up and up and up. And then at some point, you notice that they start to spread out, right? You notice, okay, my accuracy is still getting better. I'm getting more and more accurate on my training data, but it's no longer tracking with my validation data, which I'm not looking at. And so, but that makes me concerned, right? It means that when I actually go to new data, I'm less likely to do as well as I'm doing in the training set. So some of what we're going to be talking about for the next 2 days is how do we deal with this? There's this notion of regularization. Like, how do I encourage a network to learn general things that will actually apply to new data and not just memorize the training data that we give it? So then, I forget if I actually put this in here. I guess I didn't. So I called this section, right, validation and test sets. Really, best practice is to have this validation set that you're looking at sort of as you're going, and to also have some other data points that you never look at until you have a model that you think is good. And then when you have a model that you're happy with, then you look at that test set, hopefully, in theory, ideally once. In practice, rarely just once, but sort of infrequently, so that you can see, okay, how well do I actually do on new data points that I've never looked at before, right? I've never used them to tune parameters. I've never actually fed them into my training mechanisms. And if I do well in the test set, then I'm happy. So again, as we go through the examples, we'll see this in practice. So roughly speaking, your network is always going to be in one of two modes, right? One mode is called underfitting, where it's just not fitting the training data very well, right? And what it looks like is my training accuracy is just low, right? I want to classify things, and I'm only getting 48% of them right. And in my application, I need 90% accuracy to be useful. So then, fine, I'm not happy. And so what do we do? Again, we'll see this. I think you'll get more of an intuition as we play with it if you haven't done machine learning before. But basically, if the network's still getting better on the training data, then just keep training. And if it's not getting better, then you get into more complicated things a little bit. You can try more layers. You can try more bigger layers. You can try tweaking various parameters that we'll talk about. And then if that doesn't work, then you have to actually sort of be smart and use a different kind of network, or be creative in some way. Other problem is overfitting. This is where the training accuracy is great, right? And you're happy with it, but your validation accuracy is not so great. Or in particular, if they're diverging, right? So if I look at just my training data, I'm getting 80% accuracy. Maybe that's good enough. But again, I don't care about the training accuracy really. I care about how well it generalizes. If I look at validation, it's 40%. Okay, I'm not happy. So what do I do? The simplest thing to do is to just add more data. Typically, if you train on more and more data, your algorithm has less opportunity to kind of memorize particular details of your training data, and instead has to learn things that are more general. The other thing you can do is you can try to figure out how do I penalize the learner and make it, again, to try to encourage it to learn better things. And so there's some tricks that are, well, some of them are actually theoretically justified. Some of them just tend to work pretty well. One is saying, look, if I have really, really, really large weights, that tends to be a sign that you're memorizing, right? So if you think back to our picture, if I have 1,000 pixels coming in, and like it's decided that pixel 750, if that one's positive, then it's definitely an A. That's probably an artifact of my training data and not actually a good feature. So what you can do is you can say, look, add to my error function some multiple of how big the weights are, so that if they, it encourages it to keep all the weights relatively even and not look at any one particular thing too much. Another thing that we're going to see is kind of magical. It's a recent breakthrough called dropout. Basically just says, randomly get rid of half your edges, right? Like set half your weights to 0 as you're going through this batch. And the next batch, set the other half of your weights to 0. And that's crazy, right? You're learning all this stuff, and now you're just getting rid of it. But what it makes the learner have to do is not rely too much on any 1 or 2 or 3 weights being there, right? Because it has to learn general ways to compute the right answer, even if half of my inputs aren't present. And this turns out to be incredibly powerful at making these really, really big models that could easily memorize inputs not do that. And there's some other things you can do, which we'll talk about later with convolutional networks, et cetera. Andrew Ng, who's one of the big shots in sort of deep learning, Stanford professor, Google Brain, Baidu, head of deep learning, et cetera. He just left Baidu recently. Has this great analogy that I thought I would steal of rocket ships and rocket fuel. And so this is like 50% of deep learning tuning is this model explains. So if you want to go really far, if you want to solve a big, hard problem, you need a big rocket ship. And if you have a big rocket ship, you need lots of fuel. So the network is the rocket ship, and the data is the fuel. And roughly speaking, right, if you're underfitting, if you're not getting far enough, you can't like get good results. You need a bigger network, typically. So just increase the size of your network, add more layers, make them bigger, and you'll do well. But then overfitting, if you have a big enough engine, but you still can't actually get good generalization, you need more data. So kind of the bigger your network, the more data you need. And roughly speaking, if this method works, like often this method will actually work. You're like, you know what? I'm getting good training accuracy. It's not generalizing well enough, but I can pay someone $100 and get lots more data. I just throw that in, and it fixes the problem. When that doesn't fix the problem, then you have to get more clever. And that's the other half, right? Is the more creative. Like, well, it's too expensive. I don't have $100,000 for one of those cool NVIDIA toys, et cetera. What do I do? How do I make more efficient use of a small amount of data? And therefore, how do I make a smaller network? Right. There are lots of different variants on neural networks, right? So far we've seen the perceptron is basically that linear regression model, where you just have your inputs, some weights, and an output. And we've seen this feed-forward network where you have your inputs, some weights, an intermediate layer, maybe this happens many times, and an output. But then there's all these different things, some of which we'll talk about today and tomorrow, some of which we will not. Right, so autoencoders we'll talk about tomorrow. You can do recurrent networks. You can do, well, I guess deep feed-forward is up there. LSTMs you mentioned. We'll talk about that later, et cetera. And there's more convolutional networks and deconvolutional networks and blah, 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 right? So goal, again, for the workshop is to have you understand enough about this stuff that you can go learn more about these. If you do want to get that broad picture after the workshop, I would encourage you to actually go look at this particular this chart. It's called the Neural Network Zoo. And it has like a 1 or 2 paragraph description of each of these on their site. So hopefully you can follow those after the workshop. But yeah, lots of variance of exactly how you structure the units and how you train. So some things that we'll talk about next, right? That we haven't covered yet. Sometimes we know we can make assumptions about the data. For example, in visual data, things are close together are probably more relevant, things are far apart. How can we take advantage of that? We already briefly mentioned sometimes our inputs are not a fixed length vector, but say a sentence, which can be of any length. Sometimes our outputs is not just a single classification, but I want to generate text or audio or whatever else. How do we deal with that? And then tuning. Okay, so how do I decide how many layers, how many units, what optimizer, et cetera, et cetera. So I guess, yeah, so I'm gonna, well, if you have questions, definitely ask questions. In the meantime, I'm just gonna switch to the next set of slides. Where's my mouse? Yep, go ahead. So far our network says, like, look, we're going to have a 28 by 28 image as input, and so we had one weight for each of those pixels, and we have a way to compute a classification. But sometimes the input to my network, the thing I'm trying to classify, for example, isn't always the same size, right? So if I try to, the simplest example is if I want to have images of different size, then you can just resize them to be the same size. But if I have sentences or audio or stock market data, sometimes I can just insist, fine, you know what, I'm going to use the last day of data, and it's some fixed number of data points. But if I'm trying to read the sentence, that can have one word or 100. And so far we haven't described, like, what do I do? I need to have a weight for each of my inputs, right? And so if I don't know how many inputs are going to be, like, how do I pick the weights to deal with the fact that there could be different number of them? Does that make sense?
Talking about like text, for example, if you're doing sentiment analysis, you give a statement, and I ask you whether it's positive sentiment or negative sentiment. The text need not be fixed, right? You can put in as many words as you want. So that won't be an example for fixed length vector. But if it's like financial data or any kind of data where you have just a fixed set of cells you can put in data in, and then you're asking, I'm going to give you X, Y, and Z. Tell me what the outcome would be. That would be like an example of a fixed length vector.
Other questions before we move on?
How are we doing in terms of pace?
You're probably bored, but hopefully you'll stop being bored soon. I said you're probably bored because it sounds like you know machine learning already in general, but
I know already.
But we're getting to actual deep learning things now, so hopefully it'll be more new. Make sense? Okay, so let's actually look at some code, right? So that's this next section. How do we actually do this, right? We can play with the little toy thing in the browser. You can draw pictures of circles in PowerPoint. But let's actually run some things. And part of the idea is to sort of get a better grip on what it actually means to look at, training validation sets, these learning curves of how your network goes over time, how to tune parameters, et cetera. Right, so first question that you might be faced with if you say, I want to do neural network stuff is, okay, so how do I do it? Which of these frameworks do I use? Do I build my own? Don't build your own. Unless you want to learn how it works, then build your own. But for production use, use something else. So yeah, there are lots out there. I'm not even sure it's worth discussing them too much. For the most part, like the big companies all have one, and then various research labs have one. Some of them are more well maintained than others. High level points to make, I guess. TensorFlow is probably the one that has the most traction, I would say, right now. It's open source by Google. They know what they're doing in terms of AI. It's really set up for like large-scale production use. So it can do distributed training on a cluster of machines. You can deploy your model onto a phone. You can run it, obviously, on a regular server. It does all the GPU acceleration, et cetera, et cetera. So it gets a real production-ready framework. It's pretty complicated at that full scale because it can do all these different things. But it's popular. Microsoft has one that's, I think, has some traction. Facebook has Torch. They also obviously get some traction. They're all open source because I think they're all trying to get people to like basically do free work for them and figure out how to make their systems better. Because ultimately they have the data and you don't have the data, right? So even if Google gives you all of their code, you still can't match their results without also having, you know, a trillion labeled examples that they have, and you don't. Keras is an attempt to solve two problems. One is just to make it easier to do sort of standard things, right? So if you're saying, I want a standard network with 2 layers of this many units using a standard, you know, cross entropy metric, et cetera, like I should be able to write that down on a slide rather than on many pages of text, of code. So it's a high level interface. And the other thing it does is it abstracts away the backend. And so you can actually write the same Keras program and run it on top of a TensorFlow runtime or a Theano runtime, which is sort of one of the older academic open source frameworks. And I think they're now adding CNTK and I forget one of the others as well. So it kind of separates you out from the under the hood improvement. And so if someone comes along next year and says, look, you know, CNTK is now way faster than all the others, you can just say, okay, now use the CNTK backend and run on that. Or if somehow you get, you know, if Azure has built-in support for CNTK and you want to run on Azure, you can use the same code. So we're going to use Keras as the primary thing. I think I'm going to show a little bit of TensorFlow code. Lots of others out there.
Just curious, anyone use Keras?
Which one? Have you used any of the others?
No, I used only this Keras.
Okay.
I used Keras once,
Mhm.
using TensorFlow as a backend, but that's once.
Okay, we'll just play with it a little bit. Yeah, it's certainly. It seems like most people say, look, that's the place to start, unless you have a good reason to do otherwise, which sometimes you do. I guess, yeah. So high level, they handle a bunch of the low level stuff for you, like dealing with the ridiculosity that is doing numerical math with floating point numbers, right? Where 2 + 2 is approximately 4. And in particular, where like small numbers are hard to distinguish from 0, et cetera. Getting these things to actually work well and fast on GPUs is a lot of work. They do that for you. As new methods come up in research papers, et cetera, people say, here's a better way to do gradient descent. They can build that for you, and you don't have to mess with it. To choose one, it's really a standard text selection process, really. If you're planning to use this for some real application, right? Like, what's your IT department going to support? What language do you want to use? If you're already in some infrastructure, do you need to scale this thing, or are you just playing on your laptop, et cetera? Do you care about ease of deployment for production use? Yes, for maybe even real data science applications where you're just building stuff where the output is, presentations to executives that maybe you don't need to deploy to production. So I'm not going to get into that. You can ask me offline if you're interested. Yeah, I'm going to just skip this, right? So Theanos is one thing that Keras has always supported. TensorFlow is Google's. Keras is cool. We're going to look at it. So let's look at some code. First toy example, right, is just to get it. It sounds like you guys have already looked at Keras, but still, let's just get on the same page. Let's build a really, really simple model, right? 2 inputs, A and B, or x1, x2, and we're going to make a little linear. We're going to generate some data from this model, right? So 3A plus 5B plus some noise. And we're going to try to fit it, and then we're going to see what happens, right? So even this will already actually give us some sense of how we can get into trouble and what does and doesn't work. So there's a few ways you can do this. This doesn't. How do I do this? You can use the data science experience and actually download, like, get these things and run them live if you want. Right. So I have it open here, I think. I'm not going to run things just because I have things pre-set up. But yeah, you can use it here, or you can also just download the code. And if you have Python and Keras and stuff installed, you can play with it locally. If you do want to play with DSX, maybe at the next break we can go through how to set it up. You need to get some helper libraries, etc.
For the DSX, Drexula is going to stop by at 11:30, and he's going to give like a half-an-hour orientation on the DSX.
Oh, that is good to know.
Yeah.
Okay, so we'll have a demo of DSX in a bit. I just meant for setting up our stuff as well. Okay, so I'm not going to read every line of code because you would die from boredom. But I'll try to point out the interesting high-level things. First, most important question is, can you read that? Or should I make it bigger?
I think a little bit.
Is that okay? You can read that? Okay, just checking. Standard Jupyter Notebook stuff, right? Import NumPy, matplotlib, etc. So Keras. Keras has a number of different ways to sort of define the model. And when you're defining the model, you say, I'm going to have layers, right? Layers of these units. For now, we're going to have just dense layers. Soon we'll see others. And then we have activation functions. So there's this activation class that we're going to use. And then for optimization, there's a bunch of variance and gradient descent. In this case, we'll use one called RMS prop, which again, let's not worry about what that is for now. It's basically gradient descent. There's some helper functions I defined to make life easier. And here's our model, right? So this is well, it's not deep yet, but it's a network. Sequential model. It's going to have one layer, dense layer with 2 inputs and 1 output, right? So what is this? You can visualize it. Not very interesting, but it gets more interesting as you have a bigger model. You can print out a summary, which, let me just run this locally. Right. Okay, I tweaked things just a little bit locally. Fine. Right, so generate data first before we look at it. Right, so I make 100 samples. Right, so I have x1, x2 for each of those 100 samples. I have some noise, 100 noise values. I just add it all up. So 3 times x1 plus 5 times x2 plus the noise. That gives my values. You can print it out and look at it. Did this become small again? It's okay. Yeah, right. So we have a bunch of numbers, inputs, outputs. I'm going to try to predict that. First, plot it just to look at it. So we can see it looks, it's in a plane, which is what we expect. It's a little bit noisy, which is also what we expect. And so fit, how do we fit? Keras is great because it's just a one-line thing, right? You say, look, fit my model, which I defined above, to this data. So the data is my x's with these values. So that's my y's, right? Given each of these x values, so I have 100 of them, I want to predict the value I'm giving it. You give it a number of epochs. So an epoch is a full pass through all of my data, right? So if you're doing, and I guess there's batch size, right? So this is saying go 32 points at a time. Take the first 32, the second 32, the third 32, and then the last 4 in this case, because we only have 100 points. And that's one epoch. Right? So I went through all my data, I made a bunch of updates to my model, and then do that again and again and again. The TensorFlow playground, as we saw, if you just hit train, it just doesn't stop until you stop it by hand. Here, that would, isn't as good of an idea. So you say, look, run for this long, and then I'm going to see what it looks like. So Keras will print stuff out as it goes, and it's giving us, a metric of how good it's doing, right? So what's the error between the predicted labels and the actual labels on my training data after I do one pass through data, et cetera, et cetera. It returns this history object, which confusingly enough has a history element. So history.history is the dictionary that gives you the various metrics. In this case, just loss. If you were doing classification, you also have accuracy, et cetera. And so I have a little function that I made just to plot this. Right, so you can see, okay, great, loss started at 19.5 and went down to 18. What's something you notice from this curve? It's still going down, right? So it seems likely that if I keep training, it's going to continue to go down. So this is, the first example of how do I tune these things? Like, well, you watch the training curve. If it's still going down, I can keep training. So I'm going to keep training. And I tell it not to print out 1,000 lines, but let's just train for 1,000 more epochs. Because this is a toy data set, it's fast, so who cares? Why not? Right? And so you can see, okay, great, it keeps going down, and at some point it stops going down quite as quickly. This is a pretty common type of curve that you'll see, where your model sort of gets better and better, and then stops improving too much. So then there's a evaluate function. I just printed out the doc string for it, but basically just pass it data and values, and it tells you, how well you're doing, what your loss is. In particular, right, in this case, because it's a toy example, I pass it the same data and values we use to train. But in general, you could pass it your validation set or a test set and see how well you're generalizing. You can get the weights out of the model. Note that how many parameters are there? Right, we had 2 input dimensions and 1 output. 3, right? So we have a bias, right? So the model is, x1 times weight 1 plus x2 times weight 2 plus that bias term. That basically means that your linear separator doesn't have to go through the origin. Right? You can move the plane. And so it learned the model. Even after 1,000 things, right? It's not really getting better anymore. And here's the model learned: 2.5a plus 2.65b plus 1.3, which is not what we use to generate data, right? We use 3a plus 5b or plus 0, or plus noise, I guess. But noise had a mean of 0. So if instead of doing that, I can actually set the weights by hand, right? So here I say, okay, you know what? Let me just put the correct answer in and see how that does. 3, 5, and 0 bias. And it actually does give me, right? So here is my loss that it learned. Here's the loss that you get if you put in the correct answer. So it's actually lower, which is interesting, right? So even with all that training, it didn't actually get to values that are better. This is sort of that local minimum problem. Even with just 3 parameters, it couldn't adjust anymore in the right way. So here I just double check that this is in fact the loss that I told it to use, the mean squared error, no data points. Before there's a couple of points I wanted to make here. The first one was it took like 400 epochs to learn 3 parameters. That's weird. So why did it do that? And one of the things that really affects how fast your network learns is this parameter called the learning rate, which is basically how far you step. Right? So again, intuition to have is if you're doing this gradient descent, so I'm trying to walk around in these beautiful green hills and find really low points with low error, if I'm taking steps that are just tiny, 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 tiny steps, I'll get there eventually, but it's like forever. At the same time, if I look, okay, so downhill is that way, and I jump a mile, then that's not going to work well either, because if the local minimum was like 100 yards in front of me, and I just jumped a mile ahead, I'm going to be in some completely new part of the space and not actually, basically randomly flailing and not doing descent. So you're always having to trade off, like, how big of a jump do you take? And how do you pick? Well, typically what you do is you look at what people have tried and start with that and then experiment. So you try a few different values and see what happens. So I tried a different value, right? The default, the Keras uses is 0.001. So I'm going to say, you know what? Let's go 100 times faster, 0.1. So now, right, we still start at loss of 19, but very quickly get down to loss 2. Whereas before, it was like an 18.8 after 10 epochs. So flattens out really fast. And the other thing I can do is initialization, right? So in this case, I know what the right answer is. In general, you don't know what the right answer is, but you might have some hypothesis that it's sort of closer to this as opposed to that. And so initialization also matters, right? So if I initialize my network, so here I'm going to put learning rate kind of in between the two. Typically, you use log scales, right? So factors of 10 are good. 0.01, but now I'm going to actually initialize it at the right model and fit it. Here's a funny thing, right? The error actually still goes down from the correct answer. Why is that? Because of the noise, right? Because the model isn't actually 3x plus 5y. It's that plus noise, and so it's actually fitting the noise. Do we think the model it ended up with here is better than 3x plus 5y for generalizing to new points? No, right? So even here, we already have a little bit of an overfitting problem, where if somehow you knew to stop here and not keep going, you would actually get a better model. So this is something that we're going to see over and over again. All right. So let's look at a real demo. Yeah, so we're going to look at this image classification task that we saw in the slides earlier. We're going to have load the data, try a simple network, and try a slightly more complicated network. I'm just going to use my local version because it's faster, but feel free to look at the DSX version if you want. Where was this? Get rid of that. Get rid of that. Okay. So all the same sort of preamble. Now we're also adding in a dropout because we're going to try that. Yeah, I've pre-set up convenient sort of Pico, which is basically an archive file that Python knows how to read, the data set. So we're going to load it. And as I mentioned a little bit earlier, you want to split your data into train, test, and validation. So I already did that. This function will give me a bunch of training examples, right? So X and Y pairs, a bunch of validation examples, and a bunch of test pairs. How many are there? 50,000 training images, 10,000 of the other two. This is, again, standard data science-y kind of things, not really deep learning, but look at your data before you start feeding it into complicated models, right? So what does it look like? Here's one label, or one image rather. Looks like a G. Right, the label for that image is 6, which makes sense if A is 0 and B is 1 and so on. So that's just double checking things. We can plot a bunch of examples to see what we're looking at. Right, here's our data set. Most of it seems pretty reasonable. If you look closely, there's some weird things, right? There's some empty pictures. I don't know what their labels are, but clearly we're going to have a hard time getting good answers on that. There's some other things that just look random. there's a euro symbol right next to it. There's some weird blob. I have no idea what letter that's supposed to be. So just, what this is telling me is I'm not going to get 100%. And I better be okay with that, right? Because there's no way to get 100% of this. This one's kind of fun. I don't know what that is. Right, so you can look at the pixel values. They're between negative 0.5 and 0.5. That's handy. Actually, I guess brief aside, right? Typically, you initialize your weights to be small random values, like between -1 and 1, something like that. And our activation function typically has a transition point at 0. So it's better if your data also is small values, ideally sort of positive or negative. So we're going to see this over and over again where we kind of normalize things. Yeah. So the pickle file already has the values. Negative. I forget which ones. I guess negative 0.5. Let's see, this is more white, right? So this must be white. Negative 0.5 is white. This is black. For visual data, it's very standard to subtract off the mean, divide by the variance. So you get something that's centered at 0 and small. In theory, you shouldn't need to do that. It will learn eventually, but if you sort of make things numerically happy, things work better. So we're going to train this using we're going to make these flat vectors for start. So up here, I had them as 28 by 28 images I could plot to feed them to my network. At least for now, I'm going to feed them as a flat 784 vector, like we saw in the slides. So now we have, they're still the same size, still the same number, but now they're flat vectors. And we're going to, there's this utility to make one-hot encoded labels, right? So we're going from 6 to 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, et cetera. So I convert my training labels to one-hot encoded, set some constants. And okay, I guess this would be a good time to take a break after we go through this model, right? So here we're going to have an actual deep neural network. Not very deep, but has one hidden layer. So we're going to take our input, 784 pixels. We're going to have a layer with 128 units. And we can tell it what the input shape is. We're going to have an activation function, the same one we've been using so far, right? ReLU, the linear past 0, 0 otherwise. And then we're going to have 10 outputs. So we're going to connect those 128 to 10 outputs. Why do we have 10 outputs? 10 digits or 10 letters, right? That's our output. If I'm trying to classify into 10 classes, I'm going to have 10 outputs. And we're going to use softmax to convert it to a probability distribution. So then, this is just printing out the summary. We'll look at it in a second. We will optimize this using cross entropy, like we discussed. And we're also going to tell Keras, hey, I want to look at the accuracy of the classification as well as the loss. This is just the way you can tell it to look at other things. The summary is kind of handy because it gives you, as it goes through your network, so you can make sure that it makes sense. It also gives you a number of parameters that you're trying to tune. And so this is kind of interesting, right? We're over 100,000 parameters, even with these tiny images and just one hidden layer. So it's kind of surprising if this works, but it does. So now you can visualize, right? It becomes a little bit more interesting. You have your layers, activation function, et cetera. You can fit it the same way as before. And then here, well, actually a couple of new things, right? So I'm fitting in the training data. I also pass it validation data. All that does is just makes it compute every epoch what the validation statistics are and print them out. and save it into that history dictionary, just so I can kind of log what's going on, right? It's not training on this at all, but it's just telling me how it's doing. And then at the end, this is really cheating. I shouldn't have done this for real, but you can also evaluate on other data, right? So I say evaluate on my test data and see how I'm doing in the test data. Again, in real life, I would want to fit and optimize and sort of be happy with my model before I look at the test behavior. But so now I'm running, right, on 50,000 examples. And it still takes like 1 second to pass through the whole thing. And I can plot my accuracy and loss curves. So I think maybe we'll stop after these curves, but what do we see in these curves? Yeah. Yes. So I guess 0 is isn't actually 0. It's after it's done the first pass through the data. Well, I think it's just I think it's this number, wherever it is, right? 82%. So like it's looked at all 50,000 examples once, and that's their first point.
Your accuracy is a training accuracy. Based on the training data.
Yes. So accuracy is training. Accuracy is validation.
Should start initialize randomly. It should be 10%, right?
Yes.
It's expected to be at the beginning.
So we can.
10%.
Yes.
In this case, because it's
10 classes.
10
Yeah,
classes.
that's absolutely right. So again, this is not the random initialization. This is that plus a little bit of training. But it is still interesting, right? Because I think what this is telling me is with just a little bit of training, it's actually able to distinguish these classes. And then it gets even better after that. So it is surprising, right? I mean, it is pretty good. What do we look, we're up to like 90-something% and still getting better on training. Are we happy about that? They're overfitting already, right? So yeah, I can get better and better on training data, but my validation loss is flat. And in fact, over here, it actually looks like it might even be going up. Eventually, right, as we saw with our previous example, once you start really memorizing things about your training data, you're actually going to get worse at generalizing. And so it's very typical to see these validation loss curves that kind of go down and then start going up again. And you want to stop at the bottom. Okay, so we'll continue from here, but I guess I should hand over and do DSX. But first, I'll hand off the screen.
Perfect. Can you stop recording for a second?
Yeah. So I'm going to stop the recording. 1 sec. Let me just go to the right place. All right, people on the internet, we'll be back with a new session video in half an hour or so, or we're going to record the...
No, we're going to have a session now. We'll record that session too.
Okay.
Then we'll kind of take a break for lunch.
Okay, so we'll be back in a few minutes.